Okay, good morning, everyone. It's nice to see that you are all refreshed, full of energy, even though we're almost at the end of the school. So I appreciate you hanging through almost the bitter end. We have the hard work ahead of you for your presentations tomorrow. But today, I'll give the third of a series of 3 lectures on machine learning. As you recall, the way we arbitrarily structured these topics, we first started with discriminative models where we have labeled data. And today's lecture is related to what we talked about yesterday, which is generative models, the cases where we don't have labeled data, we just have some data given to us. And the approach that we saw last time on the generative model was to try to discover hidden structures and perhaps in a lower dimensional manifold in the data by introducing these auxiliary or latent variables and then trying to learn them in some sense. For example, using the techniques of variational autoencoders, using diffusion models, and a slightly different idea, which was directly sampling from the underlying distribution, which was generative adversarial networks. So what I want to talk about today, we have organized it under what I refer to as exploratory data analysis. This term is not arbitrary. It's a term that was introduced in statistics, in the statistics community in the 60s and 70s, primarily by I would say, distinguished and prolific statistician at Princeton, John Tukey, who came up with a lot of ideas, underlying ideas that later on made their way into other disciplines, including what we today refer to as machine learning. So the topics that I want to talk about are primarily the notion of principal component analysis. The same ideas have existed in different communities under related names, Farhoun and Loeff transform and variations on that theme. And then I want to talk about clustering. I'll start with an idea that's probably the most common idea for clustering. It's somewhat, I would say, intuitive development, formation of the idea of clustering. But then you can generalize that same concept into something that is more, I would say, principled from a probabilistic point of view, and that's the notion of Gaussian mixture models. And what I want to show you is, again, with the aim, the common aim of reducing many of these ideas to some fundamental notions, and also finding commonalities, but also understanding that some techniques are special cases of others. We will see that k-means is just a special case of Gaussian mixture models. I will probably not have time to really spend a lot of time on the notion of expectation maximization, but that's really the algorithm that deals with these class of techniques such as Gaussian mixture models, k-means, because you have to invoke an alternating minimization, example of which we saw last time, to be able to solve these types of problems. I've listed a reference for reading material, and let's briefly recap so that we can ground ourselves into the objectives and the methods, the approaches that we will develop today. So in supervised learning, we had a data set. We denoted that by a set D. We have pairs of data, meaning that xi's are data and yi's are the corresponding labels or classes. Remember, yi's, we started by saying that it's a discrete set. It's a finite with a finite number of elements. So those are classes. We started with introducing all of these concepts in the context of binary classification. But classification, you can generalize it, of course, to multi-class. So it's important in terms of terminology, because I've heard that used even here, that classification doesn't mean binary classification. It means a general multi-class classification. So unless we specify binary classification, okay? So, but it's a finite set of classes. That's the setting. And of course, the question becomes, where do these labeled data come from? And the labeled data most typically come from some supervision. Could be human supervision. And you have already seen the ideas of self-supervision, and we've already talked about yesterday but the idea is of using generative models in some automated way to generate labeled data. Okay, so because if we can draw from samples, and those samples tell us what classes they belong to, then we can actually generate data that is self-supervised, essentially. Under the umbrella of supervised learning, we started with the most basic, which is linear regression. We changed the underlying probability distribution and developed logistic regression, initially binary logistic regression, and then binary support vector machine, and then we generalized both of those to multi-class logistic regression and multi-class support vector machines. And then we developed deep nets, multi-layer perceptron models as a way of generalizing the score function that we had developed and progressively had made more sophisticated to really relax all of the restrictions of linearity in the weights and all of those. And we developed this general nonlinear score function that allowed us to do general function approximations. And so we saw how we can use that in many contexts yesterday. And again, we are in the regime today where we don't have labels. So what does that mean? That means we have the set D of data only. So just think of it as a scatter plot in 2D, okay? That's the 2D example, but of course we're talking about n-dimensional space. And I have summarized some of these. So the ideas for wanting to deal with essentially exploring data is to recover hidden structure in the data. The way we talked about hidden structure last time was through implicitly looking for the latent variables. But today what we want to do is we want to actually look at what that structure may mean in some statistical sense, okay? And many of these ideas, of course, are used in a variety of applications, in particular for data compression or more broadly, dimensionality reduction. So if the data that we have, as we saw yesterday with the manifold hypothesis, typically data resides in a lower dimensional manifold compared to what we would basically just search for. You know, if you have a set of images, okay, 1024 by 1024 pixels, so you have million dimensional space, but not all of those images are going to be occupying that space. So there's an underlying lower dimensional structure. And today we essentially we have a similar goal, but with a slightly different approach for doing that. Explore or explain data. We already talked about the generative data, and construct features of supervised learning. So this is exactly what I talked about. Robert repeated that, echoed that, the idea that yes, we can generate labeled data. Okay. Object synthesis, we have already seen this in terms of generative, pre-trained transformers, for example, with images and text. And let me just briefly remind you that the three topics that we looked at, the variational autoencoders, generative adversarial nets, and score-based generative models or diffusion models or diffusion-based models were topics of yesterday. And today I want to talk about three main topics: principal component analysis, k-means, and then generalize that to Gaussian mixture models. Okay, so far, with the exception of GANs, generative adversarial networks, which was essentially a game, right? It was a game theoretic approach of drawing directly the samples that resemble from noise, samples that resemble our data. That was the general idea. And we set it up as a game. With the exception of that, all of the other approaches were based on essentially building up a likelihood function and then maximizing that likelihood. In the context of when we have just the data without labels, the maximum likelihood takes a slightly different form. We saw that yesterday as well. So we have these parameters, okay? We want to find the optimum of those parameters with respect to maximizing a likelihood, okay? What's the example? This is the example that I'm going to spend significant time on going into the details of, is, for example, if this log likelihood is a Gaussian distribution, we know that we have the two parameters, the mean and the variance, assuming that it's converted into normal unit variance. And then we just have to search for parameters theta that, and the theta in this case, it's just a vector of two parameters, right? Mu and sigma, mean and variance. So basically we have to solve for that mu and sigma that maximizes the log likelihood. That's the task. Okay. Again, I've talked about this. This is the discriminative form of linear regression. The likelihood takes the form of a conditional probability of the labels given data, but the conditional probability, that essentially that likelihood function changes its form when we are dealing with generative models, in the sense that it's the probability of the data itself conditioned on those parameters. Okay, conditioned on the parameters, and so you can see that it takes the different form. Here, the parameters are the parameters of the data inside that mean of the Gaussian. And in this case, essentially the parameters are the actual random variable of what we are modeling. Okay. And we are, again, log likelihood. We had talked about the latent variables, but I want to talk about the first topic, which is principal component analysis, which deals with the underlying conceptual idea. The goal here is that you have some data in high dimension. I'm showing you a two-dimensional example here. And the goal is to find the directions in that data. So one direction first, let's start there. The direction of highest variance in the data. Okay, that's the goal. Let's start simple. What does that mean? You're given a scatter plot. This is two dimensions. We have x1 and x2 only. Okay. And this is your scatter plot. Of course, when you can see this and visualize it, if I were to just ask you visually, what is that vector, the direction that points to the highest amount of dispersion, variance in the data, you immediately would look at this and say, well, look, it's elongated in this direction, so the vector might be this one over here. Right? And what would it look like in 3 dimensions? What would that direction look like? What would be the geometric form that would follow in 3 dimensions the direction of, if you have scatter plot of data in 3 dimensions, and you want to find the direction of highest dispersion, you would just have 2 vectors and the plane that would essentially be determined by those 2 vectors, right? And so in n-dimensional space, it's as soon as you go beyond that, it's not possible to visualize that, right? So that's the whole point of finding a way to automatically determine this in high-dimensional data. And of course, you can imagine why it's of interest to find the highest dispersion, right? That's probably one of the first things you want to do in exploring data, exploratory data analysis, is to find the direction of highest dispersion, right? Maybe another very basic thing is what we talked about in the first lecture on data analysis, which is to look for periodic structures, the harmonics, which we can obtain by essentially transformation into fixed basis expansions, complex exponentials, sines and cosines, and then find the harmonics in the data. So those are the most basic. You know, if anybody goes out there, they're given some data and say, tell me anything about this data other than what I'm looking at, those are probably the 2 basic elementary operations you would perform on. Okay, so that's the goal. How do we accomplish this? How would you, without of course, relying on your eye, given data, how do you find the direction of highest variance? Okay, very good. Eigenvector decomposition of the covariance matrix. We know what the covariance matrix is, right? Essentially, you sigma i's, sigma j's. On the diagonal, you have the variances, but then you have the cross terms. That we know. But why eigenvalue, eigenvector decomposition? Okay, they provide the most natural basis. Basis we know, basis expansion. In fact, almost everything we have done so far is a change of transformation into a new space that is spanned by a different basis, right? So, but you use the term natural basis. What is a natural basis? And what's natural about natural basis? Okay, you're saying that the covariance matrix is diagonal. The covariance matrix itself doesn't have to be diagonal. It would be diagonal if it did not have cross terms, right? I see. So you're saying that the transformation into a coordinate system, we can transform it into a coordinate system where perhaps the idea of that decomposition is just we will only have to do scaling. You change the basis, you end up with that same vectors that you represented in the original basis. Now in the new basis after that transformation, we only have to change the length of those vectors. The directions are automatically found. Am I describing it, what you have in mind? Okay. Yes, so I'll talk about it first intuitively in words because it's always useful to be able to understand things in words because that shows that we have a clear understanding, and then I'll go through the math, okay? The idea behind why eigenvalue, eigenvector shows, it gives you a decomposition into a natural basis is because think about what it actually accomplishes. What it accomplishes is that it takes your original coordinates, okay, and does a transformation, but that transformation is a special kind of transformation because of the similarity transformation, and if you recall the form that it has. What's special about that transformation? First of all, we obtain it by stacking up, by building up a matrix that's made of these orthonormal basis vectors, okay? Those are the eigenvectors. They're orthonormal, though, okay? That's the important thing. I mean, they're orthogonal to each other, and with normalization, we can make them orthonormal. And what that means is essentially, and because of that, they preserve length. So we have a transformation that preserves length. What does that mean? You have that in 2D, this is the coordinate system. Okay, this is our coordinate system. Now I'm going to change into a new coordinate system in which all the length of the vectors in the first one are preserved. They're not changed when I go to the next one. What sort of transformation is that? Yes, but geometrically, what does that represent? It's just a rotation. It's just a rotation, right? So it's not, I'm not scaling the axes in an with arbitrary scaling factors. I'm just rotating, okay? In 3D, stay at the origin and you rotate it, but that rotation is based on the actual data vector itself. How much I rotate, in what direction I rotate, that is decided by basis vectors because you solve for those eigenvectors, eigenvalues, right? Based on your data, whereas that's not the case, for example, in harmonic analysis. When you compute the Fourier transform, the basis functions are already fixed. They are complex exponentials. They are not decided by the data, okay? We already assume that based on what the notion of a Fourier transform is, we assume that our data can be expressed as a superposition, as a linear combination of sinusoids or complex exponentials with different frequencies and different scaling and possibly different phase. That's the interpretation of a Fourier transform, right? In this case, those bases, it's not the same basis. Depending on the data vector, it's a different basis, different eigenvectors, and different coordinate transformation, that rotation. And that is why it's called natural. Natural meaning that it is essentially adaptive and determined by the data that we have. Okay? So that's conceptual, but let's look at a little bit more detail so that we can understand that exactly the statement that you made earlier. So let's start with the following. We have data. Let's call that X. And we have X, essentially we have D of those data records. You just line them up in this matrix. Okay, maybe the dimension of this is, call it whatever, M or F, some n-dimensional vector. The next thing we do is we center the data. by centering the data, I mean you subtract the mean, meaning that you take mu, which is essentially 1 over the cardinality of the number of records you have, you sum of all of the x, and then just divide it by that number. This mean is, of course, not the, it's what we refer to as sample mean, because it's not the mean of the true distribution, but it's the mean of whatever data we are given, okay? The sample mean. You subtract that, and why do we subtract that, by the way? What's that? To remove the trends. Yes, to remove the trends that would unnecessarily complicate the transformation. If you think about it, what's the definition of a variance? Remember, our goal is to minimize the variance, okay? That's the objective that we have. And the variance, if you just write it out, expected value of x minus mu of x squared, the expected value of that, you expand that out, you get what? You get expected value of square root of x minus mu squared of x, right? So there is that mu term in there, but we don't want to deal with that. So you just set that to 0. You subtract it. It doesn't change anything, right? You just remove the mean. And then, by the way, a lot of times you can do that in statistics. You remove the mean and you add it up. And we'll see that here in this case as well, when you go in the reverse direction. So also, as pointed out in a conversation with one of the capstone groups, if you're working with data that has units, physical units, and those units may have different magnitude, you always want to convert your data into not only a zero mean standard distribution, but also a zero mean unit variance, which means essentially you want to make sure that you are comparing things, because you want to look at the relative influences, but you have to make sure that you standardize your data. Okay, so this is the objective function now, after we have done the pre-processing. We want to maximize the variance of a set of weights times this x bar. X bar is just our original data centered, okay? The set of weights times x and the variance of that, and there is a side constraint. We want the weights to add up to 1. Okay, that's so that they're meaningful, normalized set of weights. Okay, if I expand this W transpose, the product of weights and x bar, just put a transpose over it, expand it out, I get this expression, okay? Now, if I had a mean, this expression would have other terms. That's the reason why variance is basically just that you're squaring that quantity and you're expanding it in this fashion. And so, okay, X transpose is the covariance that we've been talking about, right? But again, it's not the covariance of the distribution, it's what's known as the sample covariance. It's the covariance that the observed data gives us. It's the best estimate, our best estimate based on our observation of data. It's empirical covariance or sample covariance. And then it gets multiplied by this W transpose W, okay? Write this covariance, which is the product of these two, as sigma. So we end up with W transpose sigma W. That's the quantity we want to maximize with that side constraint, okay? So I've just rewritten that. We want to solve this problem. And because this is a constrained optimization problem, you know, we talked about gradient descent, for example, and stochastic gradient descent, variations of those. Those are problems that are used for unconstrained optimization problem. We have looked at constrained optimization problems, but I haven't really delved into methods for solving that. There are many projection methods, Lagrangian methods, and many other variations on that theme. But essentially, this is something that you even remember from vector calculus. All we do is we build what's known as the Lagrangian, and then we build it, which means essentially you take the side constraint and you combine those two. Typically, what you add up there is a plus, but that's for a minimization. We are doing a maximization, so they can go through the algebra, but you build the Lagrangian, and then you take the derivative of the Lagrangian and set it to 0. And all that means is take the derivative of this with respect to W. You'll see the terms that you have and set that to 0. It's an algebraic expression. And you end up with sigma times W is equal to lambda times W. Now we arrive at exactly what you talked about, right? Essentially, what we have is just an eigenvalue problem that operates on these weights and the covariance and the weights. In fact, what does it mean? Immediately by recognizing this, we have the covariance, which is a general matrix, right? But we want to convert that in a way that instead of multiplying that covariance times the vector of weights. The vector of weights are our eigenvalue. It's the matrix of eigenvalues. So you can think of it as one eigenvalue at a time. But we want to change that multiplication by a matrix, namely transformation. That multiplication by a matrix is a transformation, right? We want to change it so that we don't have to do the transformation. All we have to do is scaling by an eigenvalue. So we change a coordinate transformation, okay, based on our data, and then every vector in the new coordinate, it just is going to be scaled by the corresponding eigenvalue. Okay, so which eigenvalue, eigenvector should we take if we want to maximize the variance? As a reminder, when you do eigenvalue, eigenvector decomposition, the eigenvalues are ordered, the largest and the smallest, and just in decreasing order, right? And the way to think about how to parse this question is we want to maximize this quantity, right? W transpose sigma W, which is all you do is just multiply this expression. This is a condition we are solving for to maximize. Multiply both sides by W transpose, and you end up with essentially, so this is a scalar, it comes out, you end up with lambda, right? Lambda being this product. The reason why this goes to 1 is what? Why W transpose W goes to 1? Yeah, they're orthonormal vectors, right? That's the basis are orthonormal vectors. So these are basically unitary. And so what you end up with is this becomes that this quantity we want to maximize is equal to lambda. So what does that mean? We want to maximize lambda. Okay, what does that mean? You pick the maximum of the lambdas that you have, the largest eigenvalue, and that should give you the direction of the largest variance. And how do we reconstruct that? So first of all, pictorially, I showed you this. So this is, for example, the direction of that vector. To find the direction, what if we want to find the direction with the second largest, the third largest variance, fourth largest variance, and so forth? But one more condition. The additional condition is that for each one of those subsequent directions, we want those directions to be orthogonal to each other. So we want the second vector direction, the coordinate transformation, the second direction to be orthogonal to the first, the third one to be orthogonal to both second and first, and so forth and so on. Any ideas about how we do that? Yeah, I mean, if you've already done the eigenvalue decomposition to pick the largest, all you have to do is now go to the next largest, the second one, and the third one. And that's exactly the formulation of the same problem. All you do is you change your maximization problem where you have these weights for each one of those corresponding terms, and then you have D of these weights, where each W is essentially it's your indicator function. So it is equal to 1 only when I and J are equal, otherwise they're 0. So it's essentially, you just solve this optimization problem and you work sequentially one vector at a time and you compute a matrix eigenvalue decomposition, which is what you were just talking about. So here's an example. You get this first one, you get the first one direction, and here's the second direction, that red line, which is the second largest direction of dispersion, and it is perpendicular to the first one. Okay. Now, how about a new data comes in? Suppose you have a data point over here. And the idea is now you want to project that into that space. What do you do in that case? In other words, you want to go back to the original coordinate. You have a new data. You want to project it first into the reduced dimension case, and then eventually you want to go back to the original. What do we do? Yeah, you go backwards, you go in the reverse direction, which means you collect all subspace directions. Remember, we found the subspaces with the largest variance. You collect all of those subspaces. These are the different eigenvectors, right? Each one of them corresponds to that direction. W1 corresponds to the direction of largest variance, W2, the second largest direction for variance. And so we project points into that subspace, into that compressed space. You note that by x hat, it's just basically this U matrix transpose with x minus mu, okay? And then we want to now do the reconstruction in an approximate reconstruction, okay? Because we have already projected it into that compressed space. Now we want to go back. And what we do is we approximately reconstruct the data by just call that x tilde of multiplying this U with that data. And now you add that mean that we had subtracted at the beginning, okay? All right, there's an alternate view of principal component analysis. I'll just mention it to you without going through the derivation. But conceptually, it's important, it's useful. PCA finds the axis which minimizes the sum of squared distances from points to their orthogonal projections on that axis, okay? First of all, let's parse this out. Orthogonal projections. You remember in the first lecture on discriminative models, we started with linear regression. And what did we minimize in linear regression? Think of essentially a fit of a line to a scatter plot. Yeah, the residual was geometrically the distance between each point in our data set along the y-axis, okay? But here, that's not what we're talking about. Here, we're talking about an orthogonal projection. In other words, take that data point and project it at 90 degrees on that line, okay? It's different. So there's a subtle difference, but it's important difference, okay? So we are minimizing the sum of squared distances from points to their orthogonal projections, okay? And how do we go through the derivation? So this is the way it's written, okay? Essentially, we have the same minimization constraint, the difference between data points xi, and this is what's the operator that shows you the orthogonal projection. So W transpose X is what we had for least squares, but then you multiply by W, that essentially gives you the orthogonal projection of each point onto that line. And the way we do that is you can just basically look at using the Frobenius norm, which is basically just, it's a norm that's defined for a matrix. You can define various different norms for matrices. But it essentially means just the sum of the diagonal elements of the trace of A transpose A, okay? And with some algebra, and I will not go through it line by line, if we just rewrite the objective, this is what we started with, and we expand this expression and we define some auxiliary variables, we end up with essentially showing that this corresponds to the trace of the covariance matrix times this vector, the vector of identity minus W transpose. And then we can essentially just rewrite this as, if you just expand this, the trace times I, trace of this argument times the second term, you end up with the difference of two traces, okay, of trace of these matrices. And we are minimizing with respect to W, so the first term, which doesn't have W in it, that goes out because it's not a function of the weights. So basically, we are just maximizing the trace of the expression, which is sigma WW transpose. And we arrive at essentially the exact same problem as before. It's the same maximization of W transpose sigma W. And all I'm talking about is that this is exactly what we had when we set up the problem right in this is this one here. So they're identical. Yes, go ahead. Yes, exactly. Yes, absolutely. Thanks for that reminder because it's an important one. Orthogonal projection essentially means that you minimize the distance from each data point to where you're fitting to. Yeah, which is, as you pointed out, it's not the same as the distances that are along the y direction, which is what's used for least squares. Traditionally, it is what on PCXs? Yes, exactly, exactly. That's exactly right. More? 17? Yes, exactly. Yes. Yes, the vectors are the weights for projection into each consecutive coordinate transformation that you have. Each one of them corresponds to an eigenvector that defines the coordinate transformation. And you consecutively project into that space. It's a projection operator. Yes, sure. Great question. The next slide will explain that, but let me say it in words first. So there are two intertwined goals here. The first one is to uncover hidden structure in the data, and the way we define structure was to find the directions of maximum variance in the data. That's the first goal. And if we stop at that goal, you're right. We don't need to, after finding these directions, to actually project onto those directions. The reason why project onto those directions is the second goal, which was dimensionality reduction. We want to be able to take our original data, express it into a lower dimensional space. Why? Well, many reasons. First one is compression, transmission of data. In fact, that does happen, compression and transmission over communication channels, everything that you're holding in your wireless devices, that uses the same basis. The fact that you transform your data into a lower dimensional space, you operate on that lower dimensional space, and then you reconstruct. And by the way, the example that I just alluded to that I'm going to talk about, that is exactly that. It's called face recognition or eigenfaces. Okay, you ever wonder when you show up at the airport these days, they just, you don't even have to show your ticket anymore. How do they know? What do they do with that image that's captured on a detector? So you have a CCD of pixels. Let's say you have high resolution, 2048 by 2048 pixels. So you have millions of pixels. So how do you think they verify that it's you? Any ideas of how you would do that based on what we just saw? Exactly. So one has to find the coefficients of that decomposition. So the coefficient parameters or eigenvalues is what we're talking about, right? And let me explain to you in more detail and in terms of numbers so that this makes more sense. So suppose in this case, we have faces here, right? In practice, in the example that I gave you, there are maybe hundreds of thousands of faces, okay? Now, clearly, what we cannot do is we cannot just take one image that's 1,000 by 1,000 or 2,000 by 2,000 and then compare the pixel by pixel or even region by region with all the other tens of thousands or hundreds of thousands images in a database. We cannot do that. Computationally, it's not feasible, right? So what do we do instead? One way to do that, and which is the answer of why this compression is useful, is so a set of those images, okay, each one of them, if you perform once this decomposition on, so you have basically, you have a set of images, you can compute a mean, okay, and then you can project these onto a lower dimensional space. If you have tens of thousands or hundreds of thousands, maybe you just need a few hundred eigenvectors to capture most of the variance, the variability. Remember I showed you the image, the picture from the original variational autoencoder, where automatically, this is the important, they automatically found the two-dimensional latent space, where one of them was change in orientation, because when you show up in front of the camera, not everybody looks exactly at the same perspective. Orientation, and the other one was expression, right? Change in expression. And of course, that what the assumption or the idea here is that with a reduced number of decompositions, coefficients, into the reduced space with the variances, maybe a few hundred. In this case, we're just talking about 25 eigenvectors of a whole large database. You will be able to capture most of the variability in those images. That's the idea, okay? So what do? You obtain that decomposition. You have these eigenvectors, and then you reconstruct, okay, if you want, from these eigenvectors, the images. This just shows you that you can go back in reverse direction. But for the application that I talked about, this is exactly what you talked about. Now, in the reduced space, all you have to compare is not 4,000 pixels, but maybe a handful of eigenvalues with all the other images. So all you have to do is, for example, you can have an efficient data structure in which you just compare a few of the eigenvalues with all of the other eigenvalues in the database. And it's just a scaling comparison instead of these very large matrices. And you can quickly perform that comparison and find that similarity. Of course, you have to define some similarity metric. Okay, that's the idea. Go ahead. The dimension of what reduced space you... Well, yeah, so that's always an important step. The question is, what should your model order complexity be? And it always appears in different settings. In this case, we're talking about how many basis factors represent the information that you need most accurately. And the answer is, for most problems, I mean, this is no different than, by the way, in physics, what people do. And what is that called? It's called perturbation analysis, right? So all you do is you just find how much of the energy, for example, how much of the variability is captured by how many of your eigenvalues and eigenvectors. And if you're okay, for whatever it is that you need to do, is if you want 90% of the information, maybe that is captured by the first 10 singular values and singular vectors, or eigenvalues, eigenvectors. So it really depends on what it is that you want to do with that information. In fact, this is related to the very first lecture we talked about, which was, remember, when we talked about solving an inverse problem using singular value decomposition, and the fact that if we use all of the singular values, including the ones that are very small eigenvalues, that amplifies noise. So one way to essentially deal with the noise amplification of least squares is to just do this reconstruction, not with the complete information, but with a subset that captures the salient features at the same time as when it reduces unnecessary perturbations that you end up in your data. And so another question becomes, how do you decide what your damped singular values, how many singular values to capture? And again, just to close the loop, another point I made is that with iterative techniques, such as gradient descent, you can show analytically that they work on the basis of the fact that in the first iteration, if you start with a smooth initial guess, in the first iteration, you capture the information that's given by the largest eigenvalue. In the next iteration, sequentially, the second largest eigenvalue, and so forth and so on. So one way, for example, to regularize the problem is to halt the iteration before convergence, because essentially that corresponds to reconstruction without unnecessarily small coefficients that cause perturbation in your solution. Okay? All right. So all I'm going to say here is that for singular value decomposition, it's just an efficient way of computing it. Here, the way we talked about this is that we are computing the covariance by what? By X times X transpose, okay? But you don't need to do that numerically because SVD itself already, it's incorporated, it's built in there. So you can compute principal component analysis using singular value decomposition that we talked about before, rather than just manually performing this multiplication and building your empirical data covariance, okay? Your sample covariance. That's all. Okay, let me move on to the next topic. We've had a good discussion. Are there any additional questions on this before I move on to the next topic? Yes. Yeah. So variational variables are in the context of when we are interpreting PCA in the context of variance maximization. But if you are talking about just the deterministic formulation of that problem, eigenvalue, eigenvector decomposition, all you can think about is that essentially what you're doing is that you are decomposing the original problem into a sequence of hyperplanes that are decided by your data, that a partitioning, if you will. And so the question becomes, how many of those capture most of the partitioning in the subspace that has most of the features of the original data that you have? So, but can you repeat what it is that you're asking? Is there a way to do what? Okay. Now, okay, I understand this more clearly. So you're saying that not which one gives us highest dispersion, but which one is more important. Then that becomes, the question becomes, what do you mean by important? It is in the sense of contributing to the variability in the data. That's all it does. If you want to quantify the relative influence of one variable, okay, in some system, you would have to do something that's more sophisticated than that. So that problem, of course, it's an active problem and has been tackled for several decades, but that's referred to as causal inference, where you try to understand the directionality of the x1, x2, the different variables that together build up the behavior of the system. That's a topic that I contemplated including at the end of this talk, but I realized that that's beyond the scope of what we can do. Okay? Okay, so k-mean clustering. What's the idea? By the way, I've put the reference here to the same textbook by Murphy, chapter 11. The idea is the following. First of all, let me just talk about the idea of segmentation. So we're talking about clustering. Sometimes it's used interchangeably with clustering. Here you can imagine that basically, semantically, there are different things going on in the image. Again, human mind can immediately do the abstraction. And you want to be able to figure out where are the people, where are the bicycles, and where is the background, for example. This is an example of segmentation or clustering. Okay, this is done on, of course, a color image. And how do we do that? So here's one way of doing that. So here's another example. So you have an image, okay, this image. And of course, you can generate the brightness histogram. If this is a grayscale, maybe with 8 bits, you have 0 to 55, and that's the range. And you can imagine here that, so this corresponds to low grayscale. This is black and white, and the gray, which is these leaves, is somewhere in the middle. Okay, that's just the grayscale. You have the histogram, and then you can essentially use that data, the data that you have, to build clusters. If you build clusters, you can imagine visually, in this case, you have this cluster, and perhaps you have that cluster. And if you just wanted to have essentially 2 classes in your clustering, you can just generate that result. Okay. I want to talk about k-means, the idea, and the particular algorithm for solving it. We're going to be using it. And by the way, Tomoko Matsuo's lecture will show examples of how this is used in heliophysics, the same structure that we have had in the last several days, where I talk about the conceptual underpinnings, and then you'll see some examples. And of course, in the exercise later on this afternoon, you'll have another opportunity to do this hands-on. So what's the idea? The idea in words is that we have to initialize, and this is related to Marco's earlier question. In fact, you did ask me the same question last week in a different context. And that has to do with the number k. Pick k random points as cluster centers, call them mu sub k. And the question is, how do we pick k? So set that aside for a minute, okay? Assume that we pick the appropriate k. For example, if in that previous example, if we have 3 clusters, start with k equal to 3. Of course, we don't know that ahead of time when we are given some data. But for now, assume that we do. Assign data points xi to closest cluster center according to some metric. We'll define that. Update the cluster center to be the average of its assigned points. So this cluster center shifts by that assignment, and then you compute the average, and then you repeat that process, and the stopping criterion is when no point assignments change. Every time that you make a new assignment, the amount of change is smaller than some threshold, okay? So let me show you how it works, and then I'll show you the algorithm. So in this case, it's a 2D example, and we have these 2 clusters that, again, visually, ahead of time, in this case, we know how many there are, but in high dimensions, we don't. So there are 2, so we start with k equals 2, and the red and the blue essentially imply that we pick 2 initial cluster centers. Of course, they end up nowhere near the center of those clusters initially, if they're random. And then we make an assignment. So in other words, we look for every one of these data points, we compare the distance with this center and that center. If it's closer to this center, we label it red. We say that it belongs to this cluster. And similarly for the other one. And then this is the partitioning that we end up with in that first iteration. Okay, now what's the next thing to do? This is the second part, by the way. The second part of that iterative step is we compute new cluster centers. We compute the location of all the reds, and we assign a new center to them. That new center ends up there. Okay, we do the same thing for the blue. That ends up there. And then at this point, we just repeat the process. Again, we compare the distance of every single data point to this cluster versus that cluster. Whichever is closer, we declare the corresponding partition. And so this is at the next iteration. We end up with the iteration separates these. This is essentially the distance partitioning. And then the new center clusters and so forth. And then quickly, you see that essentially you have found center clusters and what those cluster memberships are. Okay, that's an intuitive illustration. But how do we solve this? What do you think the cost function should be? That's been the recurring theme, right? We have to, if you want to solve this computationally, you have to be able to write a cost function or a loss function and then optimize it somehow. What do you think the cost function for this task, for this operation should look like? Say that again. A distance metric, certainly we need a distance metric for any optimization problem, but what should that distance be? How do we set up that distance? It's distance to that plane. Okay, yes. So yes, so basically what I'm gathering based on various comments is that we have to have the notion of finding the cluster center. That's one thing we have to find. And then we have to find the membership, which one belongs to that cluster center, right? So there are 2 tasks here and 2 corresponding costs. So the formal description is that what's known as a distortion measure is we have to minimize. Let's look at the first minimization. There are 2 consecutive minimizations here, right? The first minimization is essentially with respect to a this membership. So R sub I, which is, does it belong to this cluster or not? So it can take on only 0 and 1, right? And it, just like a Bernoulli random variable, it just adds up like a density to 1, okay? What does that mean? If it's only, it can take on 0 and 1, but it adds up to 1. That means that if you write it as a vector, it's 0, all the members except for one location in that vector. So, but that location moves because it depends on the index of which one of those clusters we are talking about, okay? So if we had in the previous example 2 clusters, it's a vector that has 2 elements, and one of them is 0, the other one is 1. If the first one is 1, it means the first cluster, but if it's 0, 1, it means the second cluster. That's essentially the way we're writing it. And we have cluster centers mu sub k, okay? So we are minimizing this inner sum over the number of cluster centers for that example, maybe k equal 2 or k equal 3. And what we are doing is that this is the distance you were referring to. So the distance is distance between each data point to the cluster center. And this is the L2 norm of that, so the Euclidean distance. We want to minimize that, but we also want to essentially minimize that whether it belongs to that cluster or not. That belong variable is by this R, and so we want to minimize with respect to R, and then we want to minimize with respect to the cluster center mu. So what does this constraint remind us of? Remember, it's appeared in the context of yesterday's lecture, right? We had alternating optimization, for example, in GANs, right? Because you had this gain that you had to essentially do an alternating optimization. And a similar thing in variational autoencoder. So this is a recurring thing. And we look at, let's break down the cost function. So this is the cost function. And an alternate optimization means that we perform the optimization in 2 steps. Step 1, we optimize for R given mu. So you fix one of those. We are making 2 searches. One search is the cluster center. The other one is an assignment, right? Does it belong to that or not? The location of cluster center, whether it belongs to this cluster or not, right? Those are the 2 things. So fix the cluster center. That's how we initialize. Remember the 2 dots, the 2 crosses that ended up in a random place? So suppose that that's what you're given. After you're given that, you are deciding if xi belongs to this cluster or the other, or any of the other ones. So that's the first minimization. Then you optimize after that for mu given R. Now you have the belongings. You know which one is red, which one is green in my example, or red or blue. But now what you want to do is you want to essentially optimize for mean. And the mean, the way we do that, the usual way is the sum, you sum it over all the data points, you calculate the new cluster centers by setting this equal to 0, solving for mu. In this case, we can just solve it analytically, which is essentially the ratio for each cluster center over the sum of total values, okay? All right, in terms of computation, yes? Absolutely. So that's a great question. In fact, I'll talk about that in a few slides. In practice, you don't use that start at random. I only set it up this way just to illustrate the fact that in the absence of any other information, that's what we can do. But in practice, actually, you almost never do that because it turns out that for these types of optimization problems, initial guess matters a lot, okay? And there are a variety of different approaches to perhaps clever ways of better initialization. I'll talk about one of them. So, and the reason for that is exactly the points that you're seeing here. Local optimum is found, and when we are guaranteed, but it's not global, okay? We don't have the condition of convexity, and that's exactly the reason that because it's a local optimum, initialization, change the initialization, you may end up in a different local minimum. So it matters. So we are guaranteed to converge in finite number of iterations. And running time per iteration, there are two operations. Assigning data points to closest cluster centers is of the order, this big O, capital O, of K, the number of clusters, the number of data points, and times the records. Change to cluster center to the average is on the order, it's not the function of the number of clusters, it's just N times D. Okay, the extensions. The first one answers your question. K-means is very sensitive to initialization. There is most commonly, one of the commonly used approaches for that initialization is a variation on Loy's algorithm known as K-means plus plus. And all that does is, instead of just assigning cluster centers at the beginning, do the assignment in a sequential way. So you assign it, the first cluster center, and then you look at everywhere else, and then you decide where the next cluster center should be assigned based on the distance between the first one and everything else. So you do that sequentially instead of just in one step initializing your iterations. It also depends on the feature space. So there are methods for kernels. I should have mentioned that in the context of PCA as well. We talked about kernels for support vector machines, right? So you can actually generalize many of these concepts by introducing these functions, kernels with certain properties that would allow you to essentially operate on not really picking features, but automatically finding the information in your data. Okay. That is, okay. The distance measure, the one that I showed you was the Euclidean space, most commonly used, but it is also possible to use other ones. The third one, the last one, which is a nonlinear distance measure, is based on kernels. So you define these general functions phi of your data, x. So in other words, a transformation into a different function space, and then performing that distance metric, the Euclidean one. And of course, how to evaluate it. If it's a generative setting, the question is, how well are points reconstructed from the clusters? That's known as a distortion measure. If it's a discriminative setting, the question becomes, how well do the clusters correspond to labels? You're actually using the difference, you have Ys, and so you use that in the evaluation metric, and that's known as purity. So those are the two different types of evaluations. There are applications, and here's an example. Just with two clusters, you can see the corresponding histogram of the image. Does anyone know what this is? Where this is? Yes, exactly. Where is the location? Where in Germany? Bavaria, very good. Okay, where in Bavaria? Very close to Austria, almost at the other side of the border. Yes, yes. So here's the image, and you have this two clusters. With two clusters, you end up with this segmentation. With three clusters, you end up with this. But essentially, with more number of classes that you add, it shows you the structure versus the maybe trees. And here, you find maybe the variation in the middle between the trees and the background, the lighter background. Okay. I already talked about some of these concepts. Spatial smoothness, you can augment the feature space to contain spatial coordinates. That's one idea. You can use this for a variety of applications. The superpixel has a 5D feature space and the corresponding distance metric. Okay. So to summarize K-means before I move on to the last topic, the pros are, of course, it's simple conceptually, easy to implement. The cons, need to choose K. There are ways to automate that. The general topic is referred to as model order selection or estimating model complexity. Excuse me, I need to take a short break and get some water. it's sensitive to outliers. And for the obvious reason. Why is it sensitive to outliers? It's the same theme as we've had before. Exactly. If you just use the Euclidean distance, you're always going to be sensitive to outliers. We can get stuck in local minima. That's the nature of the type of optimization problem that we have because it's not convex. All cluster centers have same parameters. It's not adaptive, right? So you can actually have an additional degree of freedom added, and it can be slow depending on the size of the problem. So I want to talk for the remaining 10, 15 minutes that we have about a generalization of this concept to something that's a little bit perhaps more grounded in statistics, and that's Gaussian mixture models. As it turns out, and what I want to show you at the end is that K-means is just a special case of Gaussian mixture models in which we approach the limit of zero variance. Essentially, you have these Gaussians that are at the center of each cluster, okay? But when that Gaussian, the variance gets smaller and smaller, becomes a narrow Gaussian until it becomes just a line centered, that becomes K-means. So conceptually, that's the image that I'd like to leave you with. But let's see how that comes about. Okay, so again, there are some references here. And we already talked about the formulation. So let's start with a data set DI. And we want to find, so in this case, all I'm saying is that I have a cluster data. I just want to find one Gaussian, okay, that corresponds to that data. What does that mean? It's a similar problem to us. It means that I want to find where the center of that cluster is. And I want to know how spread that cluster is. That's the simple question I'm asking right now. That's all, okay? So given a data set, how to find a theta that corresponds to the mean of the Gaussian and the standard variation. And we just minimize negative log likelihood. Okay, negative log likelihood, it means that we minimize with respect to the two parameters of the Gaussian, the negative log of the product of these likelihood functions for each data point. Why the product? What gave us the ability to, instead of just, you know, this relationship exists for just one data point, right? But now with I over the entire data that we have D records, D points in our cluster. Why can I write it as a product of lower dimensional distributions? In general, it would be a very high dimensional, D-dimensional joint distribution, right? But I'm writing it as a product of these lower dimensional distributions. Why can I do that? Independent, and one more, identically distributed. Okay, so that's the assumption that we are making. And that allows us to basically write this high dimensional distribution into a product of smaller ones. And then furthermore, by taking the log, I'm able to convert that. Essentially, right now, I'm just going to write it as a product, but I'm going to take the log. If you take the log of this expression, you have the log of the product that ends up with two terms. The first term corresponds to the argument in the exponential. You take the log, you just bring the argument of the exponential down here. Okay, so just this term comes down here because you have applied the log to this exponential. And the second one, which is here, you're going to have the log, but you have n of those terms multiplying each other, right? And basically, you can just show that it's basically n over 2. And this is the argument because it's the log of a ratio. Okay, so you change the sign, that goes up, and you have the square root, and you end up with n over 2. Okay, so that's basically what we have. And how do we optimize this? How do we solve it? We minimize its negative log. They have these two terms. And the optimality condition, again, in this case, you can actually do it analytically because essentially you take the partial with respect to the mean. And if you do that with very simple algebra, you recognize that essentially all you have to do is just write it in this fashion. Okay, you're taking the derivative with respect to mu of this term. Just bring the two out, you just do a very simple algebra, set it to 0, you solve for the mean. And lo and behold, what is the mean that we estimate? is just the sample mean. You take the average all of the data points, and that gives you the mean. And that's exactly what we did for k-means. So it's just a sanity check, right? We set up the optimization, we solve it analytically, and it tells you what the optimum choice for the cluster center should be. Then we do the same thing for the standard deviation. Again, take these terms. So you have this one, and then you have this one, these two terms. You take the derivative, they take the partial with respect to sigma, like this, set it to 0, and solve for sigma squared. And lo and behold, what does sigma squared turn out to be? Sample variance. That's exactly what you would expect the result to give you. So that's a good sanity check. Yeah, okay, no problem. Easy enough, intuitive, but what's the difficulty? I started with a simple premise saying that I have a cluster and I just want to fit the Gaussian to it. You remember the example I started with in developing variational autoencoders? You have one cluster, you can have multiple clusters, you can have a line, then you can have an embedded space, you can have latent space that you are not privy to, we don't observe, right? And what's the difficulty? The difficulty is that, of course, most data is not captured with just one cluster, with one Gaussian. So it's almost like solving the k-means with just k equal to 1. That doesn't give us much, right? You just determine the amount of spread and where the center of that cluster is. So we generalize this. How do we generalize it? We generalize it, in this case, we have two Gaussians, okay? And instead of fitting, I mean, if we were to just do what I just told you to a data that looks like this actually reminds me of the topic that we were talking about your research with the X-ray data for Jupiter. Remember, you had two emission lines, you had an instrument response function. One of them was larger, the other one was smaller. And you're looking at your data, you know that it's a convolution of these Poisson arrival photons. But then how do you actually make sense of it? Do you make a fit to just the whole data, or how do you decide on clusters? So if you have two, and you make this fit, of course, you get something that's meaningless in terms of helping you out understanding your data. But if, again, if you knew k had to be 2, which is an assumption we are still making, then you would fit two Gaussians with different mu's, with different centers and different spread, okay? And that is the idea behind Gaussian mixture model, which it just means a mixture or a linear combination of Gaussians. And of course, if you have enough of them, whatever the complexity in your data is, can be captured by this model. Okay, how do we set up the problem? We have a linear superposition of Gaussians. So the simple example of a single Gaussian that I showed you, we have to add one complexity to it. We have, instead of just one Gaussian, we have k Gaussians, okay? And of course, if we're going to add them up, and they each have their own mean and variance, but it's also the question of energy. Which one of them contributes more when you sum them all together? And you want them all to sum up to 1 in order for it to be a proper density, right? So that third parameter, now in our optimization, before we had only mu and sigma, but now we have to introduce this pi, which is essentially, you can think of it as the relative weight that adds up to 1 of each one of the Gaussians that builds up that mixture, that constructs that mixture. Okay, so the condition here, I'm saying that, so we have a finite number of clusters, and pi, when you sum it up over all of the clusters, it's 1. So for example, if you have two clusters with the same contribution in terms of the energy, the height of the Gaussian, then it's just 1/2 and 1/2. But it doesn't have to be, right? So it depends on your data. So the only thing that has changed, in addition to introducing that third parameter in our optimization, is that now we have a sum of k Gaussians, each one of them weighted by that relative weighting between 0 and 1. That adds up to 1. And these are Gaussians, each one of them. So this part from here, from the calligraphic n to the rest, is exactly the same problem that we solved before. But now we have pi, and we have a sum over it. Okay? So how do we solve that? Again, we want to minimize the negative log likelihood. or as we have seen in the context of deep nets, cross entropy. That's the name of that cost if you go to PyTorch. And so we minimize with respect to these three parameters. We have a sum, now we have a product. And that, so everything that you see here, product going to negative log, this part, this sum, and this is identical to the past, except that this function now itself is this. Okay, the sum of Gaussians. So now I have a sum and another sum inside of it. Sum of log of a sum. Okay, this does not have an analytical solution for the optimization problem. We could use gradient descent, numerical approaches to doing that, but there is a more elegant and preferred way of solving this problem, which again shouldn't be no surprise to you. It's something that we have introduced and used and visited and revisited. It's essentially this alternating minimization concept, alternating optimization. Okay, so in order to do that, I'm going to just briefly spend a little bit of time showing you something that it's almost, think of it as a review of what you saw in the case of variational autoencoders. And the whole idea of what you saw since then, the idea that there are hidden latent variables when we talk about high dimensional manifold and the corresponding low dimensional structure. Okay, in this case, the latent variable is a simple categorical variable. Remember the example that I showed you where we have, for example, a handwritten text, number 7, and the line that goes right through the middle of that could be drawn from a samples between 0 and 1. That's the range, right? Some sort of a interval you have between 0 and 1. You draw samples, and with the right mapping, you end up tracing that number 7. In this case, it's even simpler. Our variable, the latent variable z, is categorical. It's essentially either 0 or 1. It's not the interval 0 and 1, but it can either take 0 or it can take 1. Okay, and if we do that, then by the way, it just captures the notion of the first one. For each individual one, it's a Bernoulli distribution. Okay, and what happens if you have repeated trials of Bernoulli? What is that called? So, review of probability. If I flip the coin, there are only two alternatives. Okay, and if it's unbiased, one probability of getting one side is 1/2 and the other one. But if I keep doing this n times, what is the probability of getting what? If you do it, yes, you can show it long enough. But what I'm saying is that what's the probability of getting, let's say, n tails in k trials? There's a distribution that captures that, right? If you repeat it in the limit where you repeat it infinite times, and that's what he was saying. That's why it goes to Gaussian. But what I'm saying is that suppose I want to know the probability of repeating the trial. And by the way, what you're saying that it goes to 50% is because the assumption is that it is a fair coin, and the probability of each side is 1/2. But a Bernoulli trial does not need to be 1/2 and 1/2. We can call it p. P could be 1/3, and 1 minus pq could be 2/3. You know, so you can, for example, a bias coin. So in general, it doesn't have to be equal probabilities, but I'm saying that the trial is one of two possible things. Okay, and then if you keep repeating that and you want to find the probability, that distribution is known as binomial distribution. Okay, so that's basically what we are talking about here. That this is equal to 1, and that's basically what we call pi sub k, like a probability of this latent variable, auxiliary variable, equal to 1 equals pi sub k. And the probability of z is basically that pi repeated in repetitions, that whatever p is to the power of k. If I repeat the experiment twice, and each time I have the chance of 1/3, it becomes 1/3 times 1/3. That's basically all I'm writing over here. Okay. And then you can write the conditional for it. And the conditional of this is what's basically, it's the probability of x given z, which is, of course, X given Z is Gaussian because we know that we are modeling this as a Gaussian given the parameters of the Gaussian. The marginal for that, we can write the marginal in this fashion, and then we can just expand it by essentially the fact that this corresponds to the conditional times the marginal, and we just expand it that way. And then we can just replace it. Remember, P of Z has this product. I'll just put it here for this term. And the first one, the conditional, essentially the posterior has this form, and I'm going to replace it over here. And with some algebra, we end up with essentially being able to write it with the properties of this categorical variable. It's just a sum of pi k over n. And the posterior, again, I'm skipping over details, but I just want to get you the final realization of why the two techniques I've talked about for clustering are the same. So we can write the posterior with some simple manipulation, just writing, essentially expanding the Bayes theorem, okay, with total probability in the bottom. We can write an expression which is something that's known as responsibility. In other words, remember the assignment function that we had for k-means, now it becomes a soft assignment. In other words, we don't just say that does this belong to this cluster or that cluster or that cluster, but we say how much of that Gaussian, the tails of that Gaussian contribute to which one of the clusters, because Gaussian, the tails continue, right? So it becomes a soft assignment. It's not a hard assignment of is it in that cluster or not. It's how much of it is in that cluster. And that's exactly what this responsibility captures. And with all of these definitions, we minimize negative log likelihood. And there's a stationary point. I won't go through the details of it, but essentially we end up with using this posterior that I just derived. And then we compute the partials with respect to mu, with respect to sigma, and with respect to pi with the Lagrange multipliers, and we sum over all k. And if we solve this, essentially we end up with, for the first one, we end up with a mu, which is just very similar to the previous case, except that instead of just adding up the data points, we scale each data point by weighting that's given by the amount of the Gaussian that this corresponds to that given cluster, okay, the responsibility. And the variance, again, has the same sort of contribution because, of course, it plays a role about how much the tails of the Gaussian contribute to each given cluster in our data. And then finally, we solve for pi, which is essentially the nk over n. We don't have a closed form solution, but we have, again, this alternating minimization and the particular algorithm that is quite powerful. And in fact, I wanted to talk about that, but I'll leave that discussion, is known as expectation maximization. It's a two-step alternating optimization that's broken into the expectation or each step where you're updating the responsibilities. In other words, the amount of contribution of each one of those Gaussians to each one of the clusters. In the previous case, it was 0 or 1, right? We had to find if it's 0 or 1. In this case, it actually takes a value. And the M step, which solves for mu, the cluster center, the dispersion, the variance in the cluster center, and the relative contribution of each one of the Gaussians to the clusters. Okay, here's an example. Two clusters. These are remember, in the k-means, the picture is I just had a cross, just a point. But now I have a Gaussian, so you're looking at from the top, right? It just out of the screen, it has the shape of a Gaussian. And so I start with two Gaussians. It's a mixture of two Gaussians. And then I repeat the step of finding the assignments to the Gaussians and the distance, the corresponding distance. And then, of course, what happens here is that the shape of the Gaussian changes in the appropriate direction as given by the data, because it's a 2D Gaussian I'm showing, so it can get stretched in any direction, okay? And that is exactly what we are seeing over here. At the next iteration, when L is equal to 2, we have this Gaussian, and then look, by the 5th iteration, one of those clusters, it learns that the dispersion should be tighter. It gets smaller and gets centered around that cluster. And same thing happens later for this one. By the time you go through 20 iterations of expectation maximization, you end up with essentially the fit of these two Gaussians to these two clusters. Okay. And the final point that I want to make, I want to leave you with, this is the last slide, is the comparison of what I just showed you, which is the Gaussian mixture model, with k-means. And if you look at what I refer to as this soft assignment rather than membership to a cluster, but it's a soft assignment, okay? And then you just look at the limit of that assignment. If you write it in this way, and what happens, so when the epsilon goes to 0. In the denominator, the term for which this is smallest goes to 0 slowest, okay? And that means all responsibilities R sub ik's go to 0 except the one for which this one is smallest, which will go to unity, okay? So what that means is that these responsibilities become hard assignments, and its cost function can be shown to be identical in the limit to the cost function that we had for k-means. Okay, so the final point that I want to leave you with, which has been a recurring theme, is that if you really look closely at the details of the models that you're working with, you recognize that they're not disparate models. There are connections between many of these ideas. That's exactly how we develop many of concepts in both discriminative models of machine learning and generative models. So this is a broader, more encompassing model compared to k-means. In the limiting, when the Gaussians, the variance of the Gaussian goes to 0, then it becomes k-means. It's the same model. So it just captures more complexity in your model for the data. Okay, I'll stop at this point and take any questions. Thank you. Yes. Okay, so there are, of course, many different ways one could construct the answer to your question. How do I know the complexity of the data that I have? The complexity in terms of model order, right? In this sense. There are, you can think of, if in the absence of knowing anything, you can think of brute force ways of doing that, right? How would you do that? You solve the problem with k equals 1, you solve the problem with k equals 2, you solve the problem with k equals 3, you go up until you realize that which one is actually more meaningful in terms of capturing the complexity of your data. But of course, you don't want to do that. Computationally, that's not clever. There are ways of performing the same idea, but in a more computationally efficient way. For example, you could, instead of just going sequentially through each order, maybe understand or estimate the range of orders that make sense for your data. And you start from the simplest and the most complex, and then use whatever metric that you have for examining whether that model gives you the best result. Then you can go in the middle, and then you can go in the middle. For example, you can turn that search into a log of the number of searches that you have to do. That's another way of doing that. But in practice, a lot of times what you do is it's even a more, I would say, random sampling, a Monte Carlo approach, where you start with understanding the complexity, then you sample the space over which you need to perform that search, and furthermore, you come up with approximate ways of doing your fit rather than doing it entirely, for example, with the full number of iterations of expectation maximization, which with a halting the iteration so that computationally it becomes tractable. So there are many ways that you would implement that, but ultimately you would have to have the notion of how to reduce the search over possible model orders. And then furthermore, algorithmic accelerations or algorithmic clever implementations of not searching everywhere. And in addition to that, you need to have some metric that you have to define in the context of the problem that you have. each time you're looking at the clustering with some complexity to be able to establish that. But those are the, in fact, the exact same problem appears in many, many contexts in machine learning. And for example, cross-validation is something that's used in fitting, training of your data. You don't train all the data that you have. You use a subset of it, but which subset do you use? You may want to use a subset and then switch to another subset and then perhaps randomly search through different subsets of the data. Similar types of ideas appear also in solving the backpropagation problem in multi-layered perceptron in deep nets, because you don't solve the gradient descent. You don't want to do the search computationally. There's a lot of work showing that if you do a Monte Carlo sampling of gradient descent, known as stochastic gradient descent, you essentially get answers that are very close to that optimal. So it's a combination of those things: algorithmic acceleration, understanding developing the right metric, and finding in ways in which you can basically change your initial search space where you don't visit everywhere in your search.
So how do you then stop or kind of constrain the number of iterations that you're doing? Does it become kind of asymptotic where it's not moving, like you found the centers and they're not really moving around anymore, and then you say, okay, this is good?
Yes, yes, absolutely. So you remember in k-means, the criterion was that the cluster centers don't move. Of course, don't move means within some threshold, right? And but you can show, again, these are analytic guarantees that you will reach the local minimum with essentially this alternating optimization problem. You're not guaranteed global minimum, but you do reach local minimum.
Just wanna confirm an understanding. So is it true that perturbation theory can be viewed as a transformation of the dynamical system to a hierarchical coordinate system where the zeros and first and second orders are different base vectors, and the zeros order is the base vector or the direction that captures the most dynamics of the system?
Absolutely. So that's exactly an illustration of the same ideas that we were talking about in the context of principal component analysis.
Thanks.
It's a transformation. It's a transformation in this case, in the standard form. It's a coordinate transformation that geometrically has the form of a rotation. And you have these consecutive transformations into the different coordinates that capture essentially in the context of what you talked about, the dynamics.
I was wondering, in the PCA analysis, wouldn't it be more appropriate to take in consideration a distance metric like the Mahalanobis distance, which takes in consideration the covariance structure of the data, or it
Yes.
can become computationally more expensive?
Sure, but you're absolutely right. In fact, I did mention that there are many different variations on the distance metric. The Euclidean distance is the one that I would say more naturally captures the notion of the distance from the origin of a coordinate, right? It's the notion of the length of a vector. But whatever makes sense in the context, and there are many others. I talked about kernels. So you can, for example, use that. Absolutely, there are variations on the theme. There are many variations on even the PCA itself that I haven't talked about. You know, PCA has this, essentially the notion of, you're talking about fitting to linear subspaces. If you wanted to remove the notion of that linearity, that assumption in the model, there are variations on that thing. There's something called independent component analysis, kernel PCA, and Tomoko could tell you all about that. She has worked on those topics.
And about his question, when I was using k-means for selecting the number of k's, there's a method in scikit-learn. It's called the elbow method. It considers the number of the inertia, the sum of the squared distances, and it has some algorithm that does the whole thing in polynomial time.
Yes, absolutely. So just to describe the idea is that if you look at different orders as a function of which distance are you talking about?
Inertia, sum of the squared distance.
Yes. So that basically means that that curve, if you plot that, it will have the form of an elbow, right? So if you find the corner of that elbow, that probably gives you the optimum in terms of the complexity that the data have. Now, the difficulty with that, the limitation is that it will not always look like an elbow. And it will not always be easy for you to find that corner that you turn. Sometimes it may look that it moves in a smooth, continuous way, and it might be difficult for you to find.
Yeah, but they have an algorithm which searches for the elbow, like algorithmically. We do not have to see it by eyes.
Oh, no, I'm familiar with that. We also have papers on doing exactly that search. In fact, it's one of the papers that that's cited over here that goes back to 2018. In cases where you don't get the discontinuity of an elbow, or at least a sharp transition, when it becomes smooth, then you have to do something different. You have to find at what point do you call that gradient is exactly at that point. I mean, the limiting case is that if it looks flat, you don't have a gradient, you don't have a transition. So yeah, I mean, there are ways of computing that in a robust fashion, but all I'm saying is that you don't always end up in the optimum. Sometimes it can become challenging.
Okay, thank you.
Sure.
Last question for Farzad. All right, one more.
I'm using a thing called mixer density networks that mixes that combines neural networks with Gaussian mixers. So I want to know if I'm using labeled data. So I have R4 input space in 4-dimension, and in the output I have 5-dimensional distributions. Can we also use a CNN instead of a normal traditional neural network and mix it with a Gaussian mixture?
Yes, you can. Whether it's the appropriate model depends on the type of data that you want to learn from, right? I mean, CNNs are typically used for operations in which convolution makes sense. For example, for images or the type of data that you have, depending on the type of data that you're taking, certainly.
Thank you.
Okay, sounds good to me. Thank you.